Stand anywhere on Earth, in a city street, on a mountain ridge, beside an ocean, and it feels stable, solid, permanent. But that stability is an illusion born of scale. Beneath your feet lies a planetary engine that has been running for 4.5 billion years. Rock circulates, iron churns, continents drift, magnetic lines arc invisibly into space. Volcanoes breathe gases that regulate climate over eons. This is not background noise. It is the foundation of life. If even one of these systems had failed, if the core had cooled too quickly, if mantle convection had stalled, if plate tectonics had never begun, Earth might resemble a frozen desert like Mars or a furnace world like Venus. To understand why humanity exists at all, we have to look downward, from crust to mantle to core, and examine not only how these systems function, but what would happen if they did not. Quantum knowledge here. Welcome back to another informative video where we take a molten dive into the very lifeblood of planet Earth itself. If you come to like this video, like and subscribe for more exciting videos like this one. 1. Planetary differentiation. How Earth built itself from fire. Earth formed approximately 4.54 billion years ago from the protoplanetary disk surrounding the young sun. Through accretion, dust grains collided and stuck together, forming planetesimals. Those planetesimals collided further, releasing enormous gravitational energy as heat. Additional heat came from radioactive decay of short-lived isotopes, like aluminum-26 in early history, ongoing decay of long-lived isotopes such as uranium-238, thorium-232, and potassium-40 core formation itself, which released gravitational potential energy. Early Earth likely experienced a magma ocean phase, where large portions of the planet were molten. During this molten stage, heavy elements like iron and nickel sank toward the center, while lighter silicate minerals rose. This process, planetary differentiation, created the layered structure we see today. Without this differentiation, there would be no dense metallic core. There would be no geodynamics. There would be no global magnetic field. And without that magnetic field, Earth's atmosphere and oceans would have faced relentless erosion by solar wind. 2. The core, a planetary power generator structure. Earth's core begins about 2,900 kilometers below the surface. Outer core, liquid iron-nickel alloy, approximately 2,260 kilometers thick. Inner core, solid iron-nickel sphere, approximately 1,220 kilometers radius. Temperatures in the core range from approximately 4,000 degrees Celsius in the outer core to possibly 5,500 to 6,000 degrees Celsius at the center, comparable to the surface of the sun. Pressure at the center exceeds 3.6 million atmospheres. Why the inner core is solid. Despite extreme heat, the inner core remains solid because pressure increases the melting point of iron. Under immense compression, atoms are forced into a crystalline structure. Seismic waves confirm this. P waves, compressional, travel through solids and liquids. S waves, shear, cannot travel through liquids. S waves disappear in the outer core, but reappear via reflections from the solid inner core, confirming the layered structure. The geodynamo, creating a magnetic shield. The liquid outer core convects because heat escapes from the inner core. The inner core slowly crystallizes, releasing latent heat. Lighter elements, like sulfur and oxygen, are excluded during crystallization, driving compositional convection. Earth's rotation organizes this convection into spiraling flows. Moving conductive fluid generates electric currents. Those currents generate magnetic fields. This self-sustaining process is called the geodynamo. Earth's magnetic field extends tens of thousands of kilometers into space, forming the magnetosphere. Why the magnetic field is essential. Without a magnetic field, solar wind, erosion. Charged particles from the sun would strip away atmospheric gases over time. Water loss ultraviolet radiation would break apart water molecules in the upper atmosphere. Hydrogen, being light, would escape into space. Radiation exposure. Cosmic and solar radiation would reach the surface at much higher intensities. Mars provides evidence. Geological data suggest Mars once had a magnetic field and flowing water. When its smaller core cooled and dynamo action ceased, the atmosphere thinned dramatically. If Earth's core had cooled faster, or if it were smaller, humanity likely would not exist. 3. Heat flow. The planet's slow burn. Earth's internal heat flow is about 47 terawatts globally. Sources include approximately 50% from radioactive decay, approximately 50% residual heat from formation. This heat escapes slowly through mantle convection. If Earth were significantly smaller, it would have cooled rapidly. Mantle convection might have stopped billions of years ago. If Earth were significantly larger, heat retention might have been extreme. Volcanism could have been far more violent and sustained. Earth's size appears almost optimal for maintaining long-term geological activity. 4. The mantle, the circulatory system of the planet. The mantle extends from the base of the crust to 2,900 kilometers depth. Composition: mostly silicate minerals rich in magnesium and iron, dominated by minerals like olivine, pyroxene, and perovskite structures at depth. Temperatures range from approximately 1,300 degrees Celsius in the upper mantle to over 3,500 degrees Celsius near the core. Though solid, mantle rock flows over millions of years. Mantle convection, the driver of plate tectonics. Hot mantle material rises because it is less dense. As it cools near the surface, it sinks. This creates convection cells, though modern research suggests mantle convection is complex and may involve whole mantle circulation rather than neatly stacked layers. These convection currents move tectonic plates at rates of centimeters per year. Over millions of years, that movement reshapes continents and oceans. 5. Plate tectonics, Earth's unique system. Earth is the only known planet with active global plate tectonics. Tectonic plates interact at convergent boundaries, divergent boundaries, transform boundaries. These interactions cause earthquakes, mountain building, volcanism, ocean basin formation. But beyond surface drama, plate tectonics performs a deeper function. It regulates climate. 6. The carbon silicate cycle, Earth's long-term thermostat. Volcanoes release carbon dioxide into the atmosphere. Rain combines with carbon dioxide to form weak carbonic acid. This acid weathers silicate rocks. Weathering products wash into oceans, where carbon is locked into carbonate minerals. Those carbonates are eventually subducted into the mantle. Over millions of years, volcanic outgassing and subduction balance atmospheric carbon dioxide levels. This is the carbon silicate cycle. Without it, carbon dioxide might accumulate unchecked, like Venus. Or atmospheric carbon could become permanently locked in rocks, leading to global glaciation. Earth's surface temperature has remained within life-supporting bounds for billions of years, despite a 30% increase in solar brightness over that time. That stability is extraordinary. Without mantle convection and plate tectonics, this climate regulation would not exist. 7. Volcanoes, pressure, chemistry, and release. Volcanoes form primarily where mantle melting occurs. Mechanisms of melting. Decompression melting occurs at divergent boundaries. Flux melting occurs at subduction zones when water lowers melting point. Heat transfer. Melting occurs when rising magma heats surrounding rock. Eruption dynamics. Magma contains dissolved gases. As pressure drops during ascent, gas bubbles form. Volume expands. Pressure builds. High viscosity magma traps gas, leading to explosive eruptions. Low viscosity magma releases gas easily, leading to effusive lava flows. Explosive eruptions inject sulfur dioxide into the stratosphere, forming sulfate aerosols that reflect sunlight and temporarily cool global temperatures. Volcanoes both warm, carbon dioxide, and cool, aerosols the planet. 8. What if these systems failed? Let's imagine failure scenarios. If the core solidified completely, dynamo stops. Magnetic field collapses. Atmosphere erodes over time. Surface radiation increases. Complex life declines. If mantle convection stopped, plate tectonics cease. No new crust forms, no subduction recycling. Carbon cycle collapses. Climate destabilizes. If volcanism ceased, atmospheric carbon dioxide eventually drawn down. Global temperatures fall. Potential snowball state. If plate tectonics never began, continents may never have formed. Shallow coastal seas, biodiversity hotspots would be limited. Nutrient cycling would be reduced. Earth would likely resemble a stagnant lid planet like modern Venus or Mars. 9. Humanity's debt to the deep Earth. Nearly every civilization has relied on geology. Fertile volcanic soils support dense agriculture. Metal ores form in hydrothermal systems. Rare earth elements originate from magmatic differentiation. Geothermal gradients power renewable energy systems. Mountain formation influences climate and rainfall patterns. Even the oxygen we breathe may have been influenced indirectly by tectonics, which helped regulate nutrients in oceans, supporting early photosynthetic life. 10. The fragile coincidence. Earth sits in the habitable zone. But habitability is not just distance from the sun. It requires long-term climate regulation, a magnetic shield, active interior heat, chemical recycling, stable oceans. Each of these depends on internal planetary processes. If Earth were slightly smaller, slightly larger, slightly cooler, or slightly compositionally different, the chain might break. Life does not exist on a quiet planet. It exists on a dynamic one. 11. The planet beneath civilization. Every skyscraper stands on crust that floats on mantle that convects above a churning iron ocean, generating a magnetic shield against cosmic radiation. This is not poetic exaggeration. It is physical reality. We are surface phenomena riding a thermodynamic engine. The continents drift at about the speed your fingernails grow. The core rotates slightly faster than the mantle. The inner core may even oscillate subtly relative to the surface. Earth is not static. It is balanced. 12. The deep perspective. If we silence the core, we lose the magnetic field. If we cool the mantle, we lose tectonics. If we stop volcanism, we lose atmospheric balance. If we remove tectonics, we lose climate stability. And if climate destabilizes over geological time, complex life struggles to persist. Humanity's story is inseparable from the iron, rock, and heat beneath us. The planet's inner workings are not distant geological curiosities. They are the reason oceans exist, the reason continents rise, the reason radiation does not sterilize the surface, the reason temperatures remained stable long enough for intelligence to evolve. Beneath every step we take lies molten metal and circulating stone, quietly sustaining the conditions that make life possible. Earth is not merely a rock in space. It is a system, dynamic, layered, self-regulating. And without its inner engine, we would not be here to ask how it works.